Welcome to qnawire.
So this problem gives a series of vials, and they're labeled 1, 2, 3, and 4. This first vial is green. The second vial is red. The third is orange, so I'm just going to draw an O, and the fourth is yellow, so I'm going to draw a Y. And question A asks, which of these is the 4.0 nanometer vial? And so it says they have wavelengths of 2.8, 3.2, 3.5, and 4.0 nanometers. And so 4.0 is the longest. And so the longest wavelength is going to correspond with the smallest energy of light, which is red. And so 4 nanometers is vial 2 because it has the smallest amount of energy. B asks which is the 2.8 nanometer vial, and that's going to be vial 1, much in the same way. So this is the shortest wavelength, and so therefore it will correspond with the largest energy of these 4. And of these 4, green has the largest energy. C asks, gives the energy of the band gap of a 100 nanometer particle of this to be 1.5 eV. And we want to determine the wavelength and the frequency. And so the energy of the band gap is equal to h nu, where nu is the frequency. And so Planck's constant in this case is equal to 4.1357 times 10 to the negative 15th eV seconds. And so plugging that into this equation above, we get that nu is equal to 3.627 times 10 to the 14th hertz. And hertz is just 1 over seconds. And so we can determine the wavelength lambda in a very similar way. That's going to be equal to the speed of light divided by nu. And so the speed of light is 3.0 times 10 to the 8th meters per second divided by our nu, which we just found here, 3.627 times 10 to the 14th hertz. And that is going to give us a lambda of 8.3 times 10 to the minus 7 meters. And now C also asks, what type of light is this? And looking at an electromagnetic spectrum with this frequency and this wavelength, we know that this is infrared or IR light.